Okay, this is lab 2, the effects of gravity and drag. We will have two main formulas for this. The weight vector, which is going to be equal to negative mass times the gravitational constant 9.8 newtons per kilogram times j hat, which is 0, 1, 0, a y directional vector. This will go in the negative y direction. The drag force will be negative constant b times the magnitude of the velocity squared times the velocity unit vector, and this will be going in the positive direction against the gravitic forces, and the net force is going to be the weight vector force plus the drag vector force. So here's my baseball experiment. The initial velocity is 0, and because the weight and drag force add up initially to create a non-zero net force, the velocity is going to steadily increase as it goes down until it reaches terminal velocity, which it does not in this experiment, and the end time is 0.584 seconds, and this is going in the negative y direction, and you can see the graph here. So here is the VPython file with gravity only involved. The ball mass is 0.142 kilograms. The initial position is a 0 vector in meters. The ball velocity is initially a vector of 0 meters per second, and the initial time is 0. The delta time is 1,000th of a second. The gravitational constant is 9.8 newtons per kilogram, and the j hat is a vector of 0, 1, 0. While t is less than 0.584 seconds, the net force will be equal to the weight force, which is negative, which means it will go in the negative y direction, and the weight force is listed here, and the formulas for finding the updating velocity and position are as shown. And if we run the module, we end up with the ball falling like this, and the graph is as shown. So this is the gravity and drag VPython file. The initial conditions are all the same: mass, position, velocity, and time. The gravitic constant and j hat are the same. We found through trial and error that the b constant for the drag force is 0.0035, and while t is less than 0.584 seconds, the net force is equal to the weight vector plus the drag force vector force, and the weight force is negative, the drag force is positive, and they will counteract each other to eventually form a 0 net force and a terminal velocity. And if we run the module, we end up with this ball falling, and it's pretty similar to the other one. So here's my final graph incorporating the experimental position, the gravity theoretical position, and the gravity and drag theoretical position. As you can see, the two theoretical lines are nearly on top of each other. This is possibly due to the fact that theoretically the mass of the ball is so large that the drag force cannot really compete with the weight force, and so they remain pretty much the same except up near the top and near the bottom. And as you can see, the experimental position is higher, which means that the ball was slowed down in actuality more than it was theoretically, and this could possibly be because the baseball has stitchings that add surface area and roughness to the outside of the ball, allowing the molecules in the air to have more of an effect on pushing it upward. And we were asked what the terminal velocity is and if it's reached. The terminal velocity is when the gravity and drag forces equal 0 when added together, creating a net force of 0 and a constant velocity, which is the terminal velocity. In this experiment, it was never reached, but because it was too short a height that it was dropped from. But if we were to drop it from an ideal height, the terminal velocity would be reached when F net equals 0. And if we were to throw it downward initially, giving it initial vector higher than 0, it wouldn't change the terminal velocity, because once F net equals 0, it'll be at that same point. But the terminal velocity will be reached at a faster rate. And I hope you enjoyed the video. If you want to view my Python files, you will have to split it into 2 parts and play it in 2 different VPython windows. Thanks, hope you enjoyed it.